Okay, welcome back. So just a very quick, this is page 2 of Euclid's very famous book on geometry. And we're not going to go into it in detail, but I just want to mention that he talks about stigmatic. Stigmatic are just points, and stigmatic figures and rectilinear figures. So that would be a stigmatic figure, and then this would be a rectilinear figure. Okay, but what I just wanted, the reason I'm mentioning this is in a rectilinear figure, we can rethink how we name variables, and not name the points, but name the lengths, maybe the line segments x, y, and z, and we can loosely refer, like that you'd call a line L in coordinate geometry. You'd name a line with a single letter, but we can loosely say that line segments are both named, but also the magnitude of their length is also named by the same thing. And we're going to take that. We're going to use that in this question. Okay. So then as two kind of prerequisite kind of mindsets and skills you need regarding the area of a trapezium. First, it's very important that you do know where it comes from. That we would have started with a triangle with a base A and a height H, and then we would have come up with a second triangle with an upside down triangle with a base B and also a height H. And when you combine them together, you've the half from the formula, half the base by the perpendicular height. You've the two bases, and then you've the common height. Okay, and to show that, you simply draw in a diagonal. It doesn't matter if the diagonal is increasing or decreasing, whether you use that increasing diagonal or whether you use that decreasing diagonal. Okay. Now, but we need to go further. We need to look back after deriving that and say, what's the physical geometry interpretation of AB over 2? And what it is, let's say we had a length A, and just let me superimpose, let me stretch B down, drag B down, almost touching A. Okay, so the meaning of AB over 2 is the average length, which is somewhere in between having this bit. And it's the exact same as what we call the midline. And so basically what we're saying is, if we had a rectangle based on the midline, it would give us the same area as the trapezium. So the midline, and then furthermore, and what's really important in this question, and by the way, in order to visualize this question, I just want to flip our figure here, because these are our bases here. So in order to understand that, we want to flip this up. And so basically what I'm saying is, there's a baseline here. There's a midline, sorry, not a baseline, a midline here, and it's common. It's common to both. It has to be common to both because the height in this case, is that, and it's the same for both. It's the same for both trapeziums. Okay, so that's that. And then the second thing I want to do is, I want to loosely name this X, Y, P, and Q, say. Okay, and we'll call this H. So now let's get down and start answering the question. Explain why length CE is equal to length FD. So what I'm going to do is, I'm going to say this is my baseline, and I'll put in, and you basically kind of work these things out as you go along. So I'm thinking I want to name this, and let's call it M for midline. So no. Okay, yes, I will use it, but okay, so let's deal with the trapezium ABCD. Okay, the flatter of the two trapeziums. Let's deal with ABCD, the flatter of the two, this one. Okay, so basically, let's look at its where its midline comes from. It's one of its bases. The base on the right is P, and the base on the left is X plus Y. Okay. Now, the rest of this doesn't really matter. I have 2H, but that's its area, and that area has to be equal to. So I'm just going to run with, you know, this trapezium, and for this trapezium, this taller trapezium, and coming out shorter here, I'm going to have P plus Q is the base on the right, and the base on the left is X, and you can see that they're the exact same now. And divide by 2 and divide by H. Or they're not, yeah, they're the exact same. So what we'll do is we can delete common stuff from here. Kill the 2's, kill the H's. Okay, cancel the P's and cancel the X's. And you're left with Y equals Q. And of course Y equals Q is exactly what they wanted us to say. U, which implies that CE, which is Q, is equal to DF. Which is of course Y. Okay. And then we've probably at this stage got every bit of work that we need done, but let's figure out what this is. From A to G, deduce that A to G is equal to G to B. It had to be anyway, but okay, so no PQ, let's just call that R and S. Okay, to show. So do things on your terms, not on their terms. So they've asked us, this means to show that R equals S. When I say that, that really makes sense in this case, to do things in your terms, because we've defined the terms as we've done. So to show that R equals S, yes. So what we'll do is, it's basically showing that these two, oh, sorry, those H's are this. Yeah, when, okay, sorry, let me keep it down here. So now we can use the fact that Q equals Y. Okay, proven. So because Q equals Y, then we have, now we can come in and rename things. Element of Q or S, Q or S, T and U. So T will be the base on the right and U will be the base on the left. Okay. No. Yeah. Okay. Let's do. No. I don't need that. So basically, what I need to show is it's easy. I know what I want to say, but it's good, and this maybe is what makes proof difficult to a certain extent. So basically, but P plus Q plus X over 2 is equal to the midline for DABE. DABE. Now that's something you have to do, you know, just okay, for that quadrilateral. And then P plus X plus Y is equal to the midline for FABE. Oh, there's a mistake there. That should have only gone up as far as C. A midline for F, A, B, E. Okay. So they share the same midline and they share the same area. And then to share the same midline, they must intersect halfway. I'm not sure if I proved it or not, but I'm going to leave it at that. I'm going to park it.